Hi everyone. So my name is Milos. I'm an electrical engineer from Serbia, and today I'll be talking about an open source project I made called the Open Cardiography Signal Measuring Device. So this is how the actual project turned out in the end. We'll get into a lot of details along the way. So first of all, what did I make? So the first things first, this is not a medical device. This is completely experimental device. I just wanted to just figure out to demystify a bit how commercial blood pressure monitors work. It was something of personal nature, as I'll explain, and something I was also doing at university, and it just felt natural to continue this way. So I wanted this device to measure blood pressure. I also wanted to have free lead ECG so I can confirm that the pulses I'm detecting are actual heartbeats. And then I just started adding things like the PPG clamp. I made my own electronic stethoscope because I wanted to see how the manual blood pressure monitoring works, which I'll explain along the way. And I based all of this around the Raspberry Pi Pico W because the generally the community is giant around it, incredibly easy to use, and there wasn't a single problem that I was first to find. So it was really easy to fix up. And as I mentioned, it's completely open source. So why did I make it? First of all, my grandma, as most of people her age, suffers from hypertension or high blood pressure, and digital blood pressure monitor is a daily occurrence in our house. She needs to literally do it every night just to make sure that it's in the safe levels. And one thing I've noticed with some of the devices she has, because we have multiple, of course, is that they work great when the batteries are new, but that their performance gets really, really questionable with the battery draining, which is something I didn't expect from a device that's technically considered a medical device. So I wanted to demystify how all of this work, how these devices work, and I also took this project to be my master thesis project. And since again this is an experimental device and it has no commercial value, I wanted to give back to the community for hundreds of projects I followed along the way, both for these projects and many other projects, and make the project completely open source. So if anyone wants to experiment with similar stuff, whether it's electronics, code, I've also published all of the data sets I've recorded. So if anyone wants to just play around with data, they can do that as well. I'll begin by explaining what's blood pressure. So when you measure blood pressure, you get three values usually. That's the upper blood pressure, lower, and the pulse or heart rate. The upper pressure is actually the systolic, the lower is the diastolic pressure. So the systolic pressure is the highest pressure actually in the arteries, and that's when the heart contracts. While the diastolic pressure is the lowest, and that's between contractions. There is another parameter that you can find some blood pressure monitors, but rarely any show. That's the mean arterial pressure, and that's just the average pressure in the arteries during one cardiac cycle. So these are the four values that we will be trying to measure with our device. I'm going to talk about, believe it or not, the gold standard, even in 2024 when I was doing this research, but still in 2025. This is the manual blood pressure measurement. If you go to the doctor's office and he's taking your blood pressure, there's a really, really good chance he will do it with a stethoscope and with a hand pump because that's still the gold standard. So how this method works is if you take a look at the screen now, the blue line, sorry for the names in Serbia. Now I'll just describe what everything is. So the blue line is the actual pressure in the arm cuff. Here you can see that in the beginning you can see. Wait, let me just check if I have. Don't have a laser pointer or anything like that here. Sorry. You can see that the pressure is rising in the arm cuff, and later you see the deflation. While in the red color you can see the, let's imagine that's how the pressure actually looks like if you measured it directly inside your arteries. So as the pressure decreases in the arm cuff and it gets below the systolic value, you'll start hearing some sounds like banging sounds on the stethoscope. and those are called Korotkov sounds. And you'll start hearing them. They'll start getting louder, then they'll start getting the peaks will start getting smaller until one point at which they completely disappear, and that's the point at which the pressure in the arm cuff is the diastolic pressure. So the beginning of the sounds is the systolic pressure, and the end of the sounds is the diastolic pressure. The only problem with this method is that you don't get the direct measurement of the heart rate, but besides that, you get a really accurate measurement, and this is what's used to actually test the devices, how they work. But of course, the main problem with this is that you need a person who is actually going to conduct the measurement. Now I'm going to switch over to the automatic blood pressure measurements. This is you've just seen the similar curve on the last slide. This is how the pressure looks during the measurement, and we want to focus here only on the falling edge of the signal. This is it here, and if you take a closer look at the middle of this picture, you can see some oscillations. So the methods I'm gonna describe now, the main one is called Sapinski. It's the most widely known one. The thing is, blood pressure monitor manufacturers don't specify what algorithms they use, but this is like the general one, is that we need to detrend this signal, and we will get something like the signal you can see above. So you will get this, the signal above that you see with the oscillations is the signal without the trend function. And you can see that the amplitude of that slowly rises and then decreases. Now, we want to estimate using those peaks the envelope of the signal, which you can see with the dotted green line. And we need to find the maximum of the envelope. The maximum of the envelope of that signal, the time at which that occurs correlates with the mean arterial pressure of that measure in the arm cuff. So at the point, at the time point where the signal, the envelope has its maximum value, the pressure in the arm cuff is the mean arterial pressure. So from there, we need to get the 80% and 40% line, which are literally, you find the value. So for example, let's say here, you've calibrated for it to be one of the envelope. You find the 0.8 line and where it intersects with the envelope of the signal, and the 0.4 line and where it intersects with the envelope of the signal. And you find the moments at which those occur. And those are actually the moments at which the pressure inside your arm cuff is equal to the systolic and diastolic pressure. Now, this all sounds rather simple, but here's the issue. Here, for example, it's 80 and 40%, a different algorithm by a different scientist. The whole process is the same, but it's actually just 75 and 45%. And just there you can see the inaccuracies because those are completely different numbers for the same measurement. So you literally can't get the same results. And I'll touch up on that at the end of the video. So now I'm going to get into the electronics for this device. As I mentioned before, everything is designed around the Raspberry Pi Pico. And I had a similar project before I made my master thesis, and it was all hand-soldered breadboard stuff. But I wanted to make this because it was a little bit serious and just wanted to have everything in one box, essentially. I designed a bigger PCB to house in everything, and that's why I used the whole Raspberry Pi Pico instead of the RP2040 and the Wi-Fi module, because it was, of course, easier and faster. And as everyone ever, I was doing it late and finished the whole PCB in like 2 days. So I had to work quick, of course. This is the power electronics. Just to mention, you'll see some mistakes that I missed for working so fast. For example, the transistor Q5 is flipped, but I'm using this. This is my favorite chip for powering devices, the TPS63021, which is a buck boost converter, and it's a great chip if you want to use a 1S battery with your microcontroller. There is a power enable circuit, which is essentially an OR circuit that I latch using a Raspberry Pi Pico pin, so that when you turn on the device, you can actually turn it off in the software by just unlatching that pin. There is a protection circuit here, a 5-volt regulator, nothing else interesting. Further on, this is the blood pressure measurement part. So all of the things I did here, I did with reserve that they won't work in the end. And because I needed this to work so I can actually finish my degree, everything was done so that I had second options. You can see here the optocoupler, which I was intending to use with actual commercial hardware to trigger measuring and stuff like that. If my hardware didn't work out, but everything in the end turned out to work. So here you can see the pressure sensor connected to an instrumentation amplifier. I went with an instrumentation amplifier because I wanted to adjust my range, the range of the amplifier myself, so I can get the 300 millimeters Hg at 3.3 volts on the ADC. And you can see just two simple MOSFETs for controlling the electromagnetic valve and the air pump. This is the ECG module. So the ECG IC that I just did my own layout of, just followed the datasheet and went with the free lead version so that you can actually look at the morphology of the TRS complex when you record the data. This is the same chip you can see on the most common AD8232. This is the ECG module for Arduino, the small boards. This is the exact same chip. I used it before, worked great as a module. So I thought, why not do my own layout on the PCB. One thing to note here, because this is a medical device and my professor was rather strict about it and I wanted to comply with everything. To make it extra safe, this is a specialized USB isolation IC. This is what you use when you want to completely galvanically isolate your PC from your device, because your PC can be connected to 220 volts and stuff like that. So this was completely isolated in this way. And I used the power isolator IC, which is like a little small black box. Just this is the wrong component. And that's all of those things you can see mentioned on GitHub. I just want to show the original schematics because I will be redoing this board at some point. This is all of the auxiliary aux conditioning circuits that I had, because my initial plan was to use a digital stethoscope, which had an aux output that we had at university. But in the end, because I was doing everything from home, I found out that I could just make my own rather simple electronic stethoscope by putting a small piezo microphone into the tube of an old analog stethoscope. So in the end, didn't really need any of this circuitry, but did just did some tests with it. So this is not tested completely. And this is just the Pico with all of its connections, with pretty much all of the pins used up. And I've just left a lot of I2C connectors left, so you can expand the system with any new sensors, devices, and stuff like that. This is the final PCB I designed. In the top left corner, you can see with the cutouts the USB connector which is used. The smarter way to do this would be to actually, if you're using the whole Pico, is to use pads underneath the Pico to connect to the USB signal. But what I did was actually connect some wires and made a connector for the isolated USB, as you can see by D plus and D minus on the left side. Besides that, I just wanted to put everything in its own, let's say, box, because I find it easier to test circuits like this. And I had a lot of space, so as you can see, I had space for everything pretty much. This is a 4-layer board, so top and bottom are signal, middle are ground and 3.3 volts. There's no components on the bottom layer, and this is how the final PCB turned out. Now, you might recall that I mentioned that you can adjust the sensitivity or the voltage your instrumentation amplifier is showing on the pressure sensor. But now, how do you know which pressure you're actually measuring? This is where this device comes in. So this is the front of the device and this is the back. What this device is that you have two screws with two big syringes and 3 manometers at the front. And the idea is you can set constant pressure in the system. And using these 3 manometers, you can measure the absolute value of that system. And if you go through, I went for like 40 points or something like that across the whole range. And in this way, I made sure that the output of the sensor of the instrumentation amplifier actually was linear to the pressure measured. And why I used 3 pressure sensors here is, well, these old analog ones were, and I wasn't sure which one of them was good, and they weren't giving the same measurements. So I added the digital one, and in this way, two of the digital and the left one showed the same value, while the one in the middle was off. So it's pretty much redundancy, and I knew that the left one and the right one were the correct ones. So that would be that device. This is the whole pneumatic setup inside the device. So it's just a small air pump, electromagnetic valve. There is also the thing with the screw you can see at the bottom. That's actually a one-way valve. The idea with the system is that it's actually leaking air during the whole measurement, and the arm cuff is deflating through it while it's doing the measurement. The electromagnetic valve is actually triggered only at the end to let all of the air out quickly. Now, if you continue on further, this is the stethoscope I made. As you can see, it's literally just the old stethoscope, an old analog stethoscope, and I just put a small tube with a microphone at the end with the whole like amplifier circuit. Maybe I had an analog signal out and connected that to my device. This is the PPG clamp. It's a microelectronic clickboard, and it's just a communication over I²C. I just made this clamp to ensure constant pressure on the sensor, as well as to block out any kind of stray light that can come and actually affect the measurement. So here is again the final device and how it turned out. I made sure I went a little bit overboard with all of the colors, made sure everything is color coded so you don't connect the wrong connector anywhere. But this wasn't done on a Bamboo Lab using an IMS. This was done on a single color printer. I just did the tolerances really good and had to super glue in all of these into place. But honestly, I'm really happy with how it turned out in the end. I was happy. I did it a bit tedious, but a pretty nice result. Now, all of this, to actually use this device, I made my own protocol, which looks like G-code commands, where you would send like C1, command C1 with the parameters that you would need. But to make it more user-friendly, I designed the graphical user interface that you can see here, which it shows you live data for the 4 signals we're recording. And you can also do things like connect to the device, to the exact COM port with the exact baud rate, and also record the data into a CSV file for further analysis. I have a small video now so you can see how this actually works from one of my tests. Is the video playing? Yes. Now let's just that play out. This is a really, really big work in progress, and everything is manual, especially when it comes to the blood pressure measurement. And here are all of the signals. You can see when I tap the stethoscope, the big peak that shows up. And if you're not sitting calmly and moving around, the ECG won't look good, as you'll see on the red signal. But now I've turned on the air pump, and you can see that the air pressure is starting to increase. And I would just stop it at around 200. All of the blood pressure monitors do a rough estimation of your systolic blood pressure, and they go 30 over when they're pumping. So just a fun fact. And now while it's decreasing, you can see the orange signal now that it's actually starting to oscillate again. And that's actually the moment you detect the diastolic pressure, something I'll touch up on later on as well. Okay. I'll just let the video finish off, and that's when it triggered the electromagnetic valve, and the measurement is done. So let's look at the results. This is the graph you've already seen, the figure, and this is the air pressure inside the arm cuff. So we're interested in this part here. This is the falling edge of that signal, and if we filter it out using Python, this is the signal that we're going to look at, and this is the signal that we're going to analyze. Of course, this is a real signal, so there will be noise and stuff like that, but this is an okay signal for something like this, so we can analyze it. If we detect the peaks and estimate the envelope using those peaks, we get something like this. And using the method I described previously, with finding the maximum point of the envelope and finding the points at which the envelope is at 40% and 80% of that maximum value, we can actually find the systolic, diastolic, and mean arterial pressure. And I'll show you those results in the end. This is the measurement that I got with the stethoscope. So this is not from the same data set because the membrane broke on the stethoscope while I was doing tests. What I wanted to do with the stethoscope measurements is actually try and emulate what manual blood pressure measurement does, is that we detect the systolic blood pressure once we can hear the constant pulsations. And you can see that we have constant periodic pulsations from the third peak here. And that test, that was actually a pretty good estimation of the systolic blood pressure. If we continue further, we can look at the PPG clamp. So the PPG clamp works by looking at the actual blood flow in your finger. And this is a really nice way of actually increasing the accuracy of your measurements, especially for the diastolic blood pressure, because as you're pumping up the air into the arm cuff, as the pressure rises above the systolic blood pressure, you're literally cutting off any kind of circulation in your arm. As it slowly decreases under the systolic blood pressure, the blood flow starts to get turbulent. And as you go underneath the diastolic blood pressure, you get the laminar flow, and that's when you actually get the normal pulsations on your PPG signal. If we look at just the part of the signal where we're decreasing the pressure in the arm cuff, this is it. And you can clearly see that there is a moment when the pulsations are starting to happen. And this is the point where I wanted to estimate the diastolic blood pressure using the PPG. Finally, we have the ECG measurement. This is just the ECG signal through the whole measuring process. If we look at just a segment, you can see the R peaks here. And I just used the R peaks as heartbeats, essentially, to have something that I know it correlates directly to the heart rate, so I can compare all of my other measured signals. And this is the QRS complex of a single heartbeat. And now if we compare the results, on the right, you can see the commercial device. So my blood pressure was 125/75 with the pulse being 75 and the mean arterial pressure being 97. And if we look at on the left, you can see that the measurement I got was 127/83/97, with the mean arterial pressure being 97, which is incredibly good, especially considering that these are not from the same measurements, but they were a couple of minutes apart, and these are really good results. And I'll tell you some of the tolerances that generally the commercial devices have. As for the PPG and stethoscope measurements, you can see that the measurements I got are not as good as, actually for the stethoscope, they're good, but not as good for the PPG. And as for the heart rate, everything was around 72, which I just deemed to be correct. So those are the results. Thank you for listening. Just before I go to the questions, I wanted just to explain one thing I said about commercial devices. So a commercial device is considered grade A if it's in plus minus 15 millimeters Hg in 85% of its measurements, meaning it can be even worse than that. But just so you know that and as you've seen how an algorithm like this can work, these devices are great for literally estimating the pressure. They can tell you if the pressure is low, okay, or high, but using these devices to actually, I know some people do like, oh, now it's 144, now it's 143. That it's all nonsense pretty much. It's maybe a bit higher there, but you can't really tell with that much accuracy, especially because another thing that you can find in the literature is that there is no kind of any kind of a test setup for actually calibrating these devices. The only way, for example, that you know what kind of a signal there will be like a bionic arm on which you would put the arm cuff and measure the blood pressure. There's nothing like that. They would just measure on patients couple of minutes between the measurements, and that's the best there is for actually testing these devices. So next time you're actually measuring blood pressure, just take those measurements with a bit of grain of salt. If it's showing high or low, it's probably correct. Just make sure that you're not actually nitpicking and going like, oh, now it's 151, now it's 153, it's getting worse. It's probably the same, just the device is showing you different measurements. Thanks for listening. So if anyone has any questions, I would love to answer them.
Yeah, I had a few questions. So what was the hardest thing to get working correctly? Is that the air part of it, getting the pressure pump working and all that sort of stuff, or was it electronics? What do you struggle with?
So let me think about that here. Honestly, the data analysis was pretty rough for the pressure stuff because it's really susceptible to filtering also. And that's another thing that I've noticed with the device I have, with a commercial device that I have that actually shows that graph in the phone. It's really susceptible to filtering. So just by changing how I filtered the data that I recorded, you can get wide, just really, really different values. Another fun thing that I had to deal with during this development, because I ordered just one of those isolation ICs for the PCB, since it's like 9 or 10 pounds or something like that, as they were cutting the cut tape with the components, they actually cut all of the legs from one side of the IC. So I actually had to solder on like small wires to all of the literally little legs that were still poking out of the IC and connected to the pads, but miraculously the IC still works great.
So you didn't have any problem with the physical aspects of it?
With the physical aspects, not really. The only thing that was the issue was actually having to construct the calibration setup as well, because without that, I mean, you can always calculate based on the resistance of the potentiometer and knowing the stats of the instrumentation amplifier, you can calculate the gain and calculate the pressure from that. But with so many uncertainties, I just wanted to construct a device that I know would calibrate this device properly. So that was probably the most tedious part of the project.
Right, and you do more work on it, or do you have plans for modifying it or improving it?
So for now, I haven't modified anything, but I'm honestly planning on doing like version 2, correcting some of the mistakes I've noticed, maybe making a better stethoscope, and generally just working on software. One thing I also didn't mention here is that all of these algorithms are great if the heart rate is regular, but if, for example, somebody has irregular heart rate, it can literally skew all of the measurements to one side or the other of how it actually changes the envelope of the signal. So I would like to, I mean, in free time when I can, do some more research on algorithms and stuff like that.
Any other questions in the room? Any questions online? What's that?
Yeah.
I'll check the comments. Thanks for posting the link to GitHub. Glad you like the presentation. What do you mean exactly by an ultrasonic active sensor? Could you just clarify? I suppose you mean by detecting when the blood flow goes from laminar to non-laminar during the measurement. Not sure. I mean, technically, it should work like that. Could work like that, but I've seen some devices that measure on the rise of the pressure signal. They're usually measuring on the falling edge. I don't see a reason why not if you can filter out the noise from the pump and stuff like that.
What's all the hardware cost of it? So once you factor in all the different things you end up buying, what was the total cost of one of these devices you built from scratch?
Missed that. Sorry, could you maybe repeat?
Yeah, I just wanted the cost of all the components and everything to build it.
Oh yeah, that sounds great. The whole project is on GitHub. Somebody already linked it in the chat, and you can find the Google Sheet with the complete BOM with all of the components I used, Gerber files for the PCB, and everything else.
Cool.
Just answering more questions from the comments. So yeah, to detect the Doppler shift of signal when flow starts, that's essentially what I tried doing with the PPG sensor. But yeah, there are some papers discussing using just sensors like that, not using ultrasonic or PPG or light sensors, but like microwave sensors to detect changes in blood flow and actually measure pressure like that. Oh yeah, this was also featured in the MagPi magazine. Thanks for noticing. And yeah, the arm cuff positioning is important. So the usual way is to position it like a few centimeters above your elbow, and depending, even if you measure from one arm to the other, the measurements will be different. There are also some devices that measure near your hand, and all of those measurements will be different essentially. And this is why all of the readings that you get are actually estimations and not direct measurements. But an interesting thing is that even though that the pressure would technically be lower when you're measuring it closer to your hand, because there's less muscle and you're getting pretty closer. Let's say there's just a bone and veins closer to your hand. The signal is actually much cleaner, and it's pretty muffled when you're measuring it on your biceps, since there is more meat surrounding everything, let's say. But yeah, arm cuff positioning is rather important. I've just went with the standard way that all of the devices do it.
Well, any last questions?
I was just wondering where you got the inspiration for your case design that looks remarkably medical and professional.
Thanks, glad you like it. So it just started first from the PCB. I knew that I mean, from the USB connector that was isolated. And from there, I started in Fusion 360, started placing components around it, seeing the general shape, and then just started forming slowly the case around it, just keeping in mind that I'm gonna 3D print it. And this is how I ended up with the final design. I just went a bit overboard with the multicolor stuff, but I just wanted it at that level because it was my final project for the university.
You got a good mark on presentation in your thesis.
Yeah, it was a really good work. The teacher was really happy.
Excellent. Well, thanks very much for that. It was really good. Really enjoyed that. It's very good.
Thanks so much for listening, guys.
It does
Hope
look
you
really
enjoyed it.
good.